In this video, we will continue our exploration of the use of the parallel axis theorem to determine the moment of inertia of complex shapes. So what we have here is a circle that has a diameter of 75 millimeters and has this diamond shape which has been punched out of it, which is 40 millimeters by 40 millimeters tip to tip. Obviously, it's a symmetric section, so the centroid is going to be right at the halfway point of the circle, and so we have a y bar of 37.5 millimeters. And then before we get started, I figured I'd just sort of show for the sake of reference, the moment of inertia of a circle about its centroidal axis is 1 over 4 pi r to the fourth, where r is the radius, and the moment of inertia of a triangle about its own centroidal axis is 1 over 36 times the width times the height cubed, and obviously that centroidal axis is h over 3 away from the base. So with that, we can work through like we have on our other videos on how do we use the parallel axis theorem, and it's really going to be the moment of inertia of the given piece that we are interested in, plus its area multiplied by the distance between its centroid and the centroid of the entire section, or some other axis of interest that we care about, that distance squared. So how would we approach this? Well, we effectively would look at what is the moment of inertia of the circle, and then we would subtract out the moment of inertia contributions really of this diamond, which I think we can split into two triangles. So we'll draw that out pictorially, and then we can write out what the equations would be. So pictorially, we would have some circle, and obviously it has that about the x axis. Its centroid is the right in the center, and that it has some area of the circle, and this will be the x axis. It'll have some I about that x axis, and then d equals 0 because the distance between the centroid of the circle and the main centroid of the cross section, they're right on top of each other, so it's going to equal 0. So we take that contribution, and then we would subtract out the contribution of this top triangle in the void, which is punched out here. So we'll just draw our exterior of our circle using our x axis of the whole section, and then we'd be looking at subtracting out this triangle, which has its own centroid, so there'd be some distance d triangle, and obviously there'll be some area of the triangle, and it has its own moment of inertia, I triangle, about its own axes. So let's just make sure this is a minus, and then so if we've removed the contribution of the top bit of the void, we'll do the same for the bottom bit of the void. And again, we'll draw our centroidal axis of the entire section, and we'll draw that centroid in red just for consistency with our drawing up top here. And there'll be, again, some triangle that has some area. It has its own centroid, and there'll be a distance d triangle between there, and it has its own moment of inertia about its own axis. So again, it should be, we break it down into sort of this pictorial representation. It should look pretty straightforward, where we simply, sum up moment of inertia, area, and distance of the circle, subtract out moment of inertia, area and distance of the top triangle, subtract out the moment of inertia, area and distance of the bottom triangle. So that's what we look like pictorially. We'll just write it out in words, and then we can put some numbers to it. So our moment of inertia total is simply going to be moment of inertia of the circle plus a circle d circle squared minus the moment of inertia of the triangle plus a triangle d triangle squared, and subtract out the bottom one. My triangle plus area of the triangle and the distance between the triangle centroid and the centroid of the whole section squared. So now we have it pictorially, we've got it out in words. Let's put some numbers to this. And again, what we'll use is our moment of inertia of each of these individual pieces. We can then just apply that in this formula. So this is going to equal moment of inertia of the circle is simply going to be 1 over 4 times pi times 75 over 2 to go from the diameter to the radius. And we'll have all of that to the fourth plus pi times 75 over 2 squared multiplied by 0 squared. That goes to 0. That's because the distance between the centroid of the main circle and the centroid of the entire section is 0. It's that they're right on top of each other. So we have that. So then we subtract out the contribution of this top triangle. So the moment of inertia of the top triangle is 1 over, as you can see, 1 over 36 bh cubed. So the width is 40. I think we can keep that all into frame there. All right. So width is 40 and times 20 cubed plus the area of the triangle is simply going to be 1 over 2 times 40 times 20, so 1/2 base times height. And then we're going to multiply by the distance between the centroid of the triangle and the centroid of the entire thing, which is simply going to be the height over 3, since the bottom of the triangle is right on the centroidal axis of the cross section. So that's simply going to be 20 divided by 3 squared. Obviously, if the triangle was moved further up, we would have to, work out what that additional distance was to the centroid, but because, like I said, the triangle's base is right on the centroidal axis, it's simply going to be that distance of that centroid. And then we're going to subtract out, again, the bottom triangle, but you can see it's symmetric, so it's effectively going to be the same formula here. 1 over 36, 40 times 20 to the third, plus 1/2 times 40 times 20 times 20 over 3 squared. All right, let's do some simplification, and because these are the same, well, it's effectively the same as subtracting 2 of these, but we'll work out what this 1 over 4 pi times 75 over 2 to the fourth. If we crunch the numbers there, we get 1.55 times 10 to the sixth. And then that's going to subtract out 2 of these, 1, 2, because they're the same. The moment of inertia, 1 over 36 times 40 times 20 to the third is equivalent to 8,889 millimeters to the fourth. And the area times the distance between the two centroids squared is simply going to give us 17,778. We crunch the numbers and we subtract out the circle minus 2 of the triangles here. I total equals 1.50 times 10 to the 6th millimeters to the 4th. So that's all it is. So again, very similar to any of the other parallel axis theorem equations that we've done, where we just simply take, for a complex section like this, where we've got an external and a centroid, we first work out what our centroidal, where the location of our centroid is. And so for going about the x-axis, that's determining y bar. And then we just work out, for each component of the circle, the top bit of the void and the bottom bit of the void, what our moment of inertia, its area, and the distance between its centroid and the centroid of the main section is. And then after that, it's just a simple matter of sort of plugging and chugging with the arithmetic. So really the only challenging part is working out moments of inertia, areas, and these distances squared. But if you approach it in this sort of algorithmic fashion, where you just work out piece by piece, it's really hard to go wrong there. So with that, thanks for watching.